Welcome to everybody. My name is Stefano Savazzi. I'm a researcher at the Institute of Electronics, Computer and Telecommunication Engineering of National Research Council of Italy. Today we'll present a paper with title Calibration-Free Target Detection based on thermal and distance sensor fusion. The work has been partially developed within a project funded by Regione Lombardia in Milano with the cooperation of a small to medium enterprise company, Cognimade. The paper focuses on analysis and design and verification of a sensor fusion platform that integrates infrared thermal vision with ultrasonic distance sensing. So the paper first introduced in the presentation, we first introduced the system model, but it used the thermal signatures and the ultrasonic distance sensor modeling, data modeling. Then fusion model and the change detection scheme proposed for data fusion. Then we will propose a case study in a smart office environment. Now, passive infrared sensors on the left, using this paper, are able to detect infrared radiation in long wavelength infrared bands and can provide information about people presence, counting, and localization. However, such sensors are limited by time-varying changes of the background temperature and when the number of people increase. So we propose to combine this input with ultrasonic sensor that measure the distance or just the presence of the target by sending a sound pulse in the ultrasonic band towards the target and then measuring the round trip time. They are unaffected by optical characteristics of the targets, but they have limited detection distance compared to infrared. Considering the limitations, so we propose to incorporate both infrared and ultrasonic in an indoor environment to improve the robustness of the detection algorithm. First, we introduce here an autoregressive model for both induced thermal and distance signatures. First, we focus on infrared, so we have a temperature measurements collected in vector YT. We have an infrared array consisting of M thermopile elements, so M equal to 64. We target a twofold problem of estimating all the regions, so the occupancy in all regions. We have K regions depicted here. So we have key region in the space, and we monitor those regions for possible presence of the target. Then the second problem is to quantify the number of people in each region. So the number of targets crossing the field of view of the sensor. Temperature readings depends linearly on the occupancy and the number of people as follows, whereas K is the increase of the temperature as induced by the movements of the body. WT is the background temperature that is typically Gaussian distributed. For the ultrasonic sensor readings at time t, we now have similarly a vector UT that collects all the readings where key regions are defined, and then we have here each element refers to a distance measurement. We have a piezoelectric micro machine ultrasonic transducer that sends out short pulses of sound waves with the field of view of 45 degrees. Now the sensor measure the round trip time, clearly T, the round trip time T, that depends on the occupancy state, theta. While OTK is now the input raw data and measure the distance from the floor in case the environment is empty, or the distance between the target and the sensor. The proposed algorithm for fusion is based on a semi-blind change detection method whose general principles are revised here in this slide. Let generally ST be a source, a sensor source, maybe ultrasonic or infrared, and modeled by an autoregressive model with parameters collected in theta 0. So these are the automatic regression parameters of the process. Now, this process is subject to abrupt but temporary changes of the model parameters as due, for example, to the presence of the target in the area. Now, the goal is to detect the change point time and the duration of the change, so the segment, so in order to classify and identify the movement of the target. A typical solution is to use log-likelihood ratio test, but this is not applicable in our problem because we will need the perfect knowledge of theta 1, the parameters characterizing the statistical properties of the process during the change. So if theta1 is unknown, as in our case, so we don't know the statistical properties of the change, then you can use this simplification. So we approximate for small change assumption the log likelihood ratio. This approach is known as semi-blind change point detection. Using this approximation, we compute the Q-sum and then apply a threshold to detect the presence of the target. For applying change detection in our problem, we need some simplifying assumption. The first one, the automatic regression model. We have an automatic regression model for temperature measurements in each region. So YTK is defined as follows. And so we have, so it depends on automatic regression parameters, BK, and the innovation term, and the standard deviation sigma zeta. So these are our automatic regression parameters for the empty environment. Then we have similarly an automatic regression model for ultrasonic readings, UTK, the same definition. We have now a change in environment. So a subject occupying a region K alters such automatic regression parameters that are replaced by new, but in our case, unknown terms. So we apply the semi-blind change detection that is implemented for infrared and ultrasonic sensors separately first, and we obtain the Q-sum for both sources. And then we apply thresholding to these sources. The threshold are simply obtained by a very simple calibration at deployment time, or just in one calibration at the starting time of the initial time of the sensor. Here we have the algorithms. We have algorithm 1 gives information about how to extract the Q-sum from both sources. So to apply the change detection algorithm, algorithm 2 fuses the Q-sums, so the outputs of the change detection, and for motion detection. So we fuse the Q-sum inputs GTK from the infrared and the GT from the ultrasonic, as ultrasonic monitor only one region. The proposed model and fusion algorithms is evaluated through experimental measurements in a smart office scenario depicted here. The goal is to detect and count people entering and exiting to or from the entrance room. The device is here. The device is ceiling mounted and is equipped with one ultrasonic sensor and one infrared array, ultrasonic and infrared array, consisting of 64 thermopile elements. Up to 3 people can enter or exit from the monitor space multiple times. We also consider the case where a door is opened or closed when a subject is entering, for example, exiting. Opening and closing the door affects the background temperature of the room, and it is typically considered as critical setup for thermal monitoring application. The figure on the right presents an example of the raw data and the corresponding Q-sum here at the bottom for infrared and ultrasonic sensor. In the below figures, we can clearly highlight the smoothing effects produced by the Q-sum compared with raw data on top, while the target presence can be inferred by summing up the Q-sums from both sources, and applying a thresholding of the joint Q-sum, the summed inputs. The Q-sum therefore gives more reliable input for fusion algorithm. In particular, the infrared array, now shown in the table here, achieves an accuracy of 78%, while the ultrasonic sensor achieves a larger accuracy of 82%. When we fuse those information, we obtain a larger accuracy of 87% around. Notice that the infrared array performance can be seriously impaired by changes of the background temperature. However, small changes can be effectively filtered out by tuning the threshold. Similarly, ultrasonic sensor gives better accuracy performance, but it is affected by range limitations. So this is why we fuse those information. So thank you. This ends my talk. We presented a multi-sensor fusion algorithm for indoor body motion detection. The algorithm adopts a change point detection scheme that interprets body motion as a series of alteration of the raw data. And the algorithm in particular is very effective as it does not need prior information about the statistical properties of the change on the sensor reading, so it simplifies the calibration tasks. The proposed approach is being evaluated using ceiling-mounted thermal and distance sensors located in a smart office area. Fusion, the fusion process of using thermal and ultrasonic increases the accuracy according to our experiments of up to 50%. Future activities will target the validation in more complex environments characterized by, for example, non-stationary environments and high and strong and large temperature changes. So thank you. If you have any question, I'm here for the Q&A session. Thanks.